I want you to just imagine for a second holding this multi-million-dollar project schedule in your hands.
Oh, the holy grail of documents.
Right. You're standing right in the middle of a massive industrial site. Let's say a new combined cycle power plant.
Huge scale.
Exactly. And the document you've got is an absolute masterpiece of traditional project management. You're looking at this meticulously printed Gantt chart, thousands of man-hours, perfectly leveled.
Every single trade accounted for?
Yeah, every mechanical fitter, every high-voltage specialist, every pipe welder allocated down to the minute. You've got your float calculated, the critical path is glowing red on the screen, and your resource breakdown structure is just airtight.
It looks perfect on paper.
Right, it looks perfect. But then I want you to imagine that entire symphony of engineering just grinding to a screeching, catastrophic halt. The whole progress curve just flatlines.
And it's never the thing you expect.
Right. No. It's not a supplier bankruptcy or like a localized hurricane or some massive structural steel defect. The entire site shuts down because someone forgot to order diesel for the secondary lighting generator. Or, and this is even more absurd, because the site literally ran out of toilet paper for the field hygiene stations.
It sounds like, a dark joke you'd tell at a project management conference over drinks.
Yeah.
But it is actually the grim reality of complex field execution. You have this beautifully theoretical mathematical model colliding with the really harsh, unforgiving physical reality of a job site.
Exactly. And that is exactly what we're exploring in our deep dive today. We are looking into the hidden and honestly often completely ignored backbone of project controls.
Which is the systematic resource modeling of non-reusable materials.
Right. We're going to unpack this framework from our sources today that basically argues for tracking physical consumption on job sites at a level of granularity that most planners would consider absolute madness.
It's a complete paradigm shift. Yeah. Honestly. Traditionally, project controls have treated certain indirect consumables as just, background noise.
Like it just happens by magic.
Yeah, exactly.
Yeah.
But the underlying argument we're unpacking today is that this background noise is actually the mathematical baseline of your entire operation.
Now look, if you have ever run a complex project, you know this pain, but I have to be honest right up front with you.
Okay, let's hear it.
Looking at the methodology we're exploring today, my immediate reaction is that taking material modeling to this extreme is an absolute bureaucratic nightmare.
You think it's overkill?
I think it's complete overkill. I mean, the idea that we need to parametrically model every single non-reusable material in the core scheduling software, especially for indirect labor, like the site supervisors sitting in the administrative trailers.
The guys in the air conditioning.
Right. Modeling their supplies is just asking to paralyze your planning department. We have procurement teams for a reason.
That's the traditional view, yeah.
Let procurement buy the paper towels and the printer toner. Keep that granular, mundane stuff out of my master schedule. It's a total exaggeration of what a scheduler should be doing.
I completely understand that reaction. I mean, it really flies in the face of decades of standard critical path method training.
It really does.
But I'm actually going to defend this methodology entirely today.
Really? All of it?
All of it. In strict technical terms, if you want to guarantee adequate control, synchronize your supply with your consumption, and actually prevent those sudden catastrophic shortages exactly when the materials are needed most to stuff, then everything has to be modeled.
Everything. Every paperclip.
Every non-reusable consumable that sustains the project ecosystem. You cannot artificially separate the administrative supplies from the heavy construction supplies. The project is a single integrated living organism, and the math just has to reflect that.
Okay, so that is the tension we're navigating today. Are we looking at some myth of total project control chased by overly enthusiastic software engineers? Or does the secret to never missing a deadline actually lie in mathematically modeling the most mundane details on the site?
It's a big question.
It is. So to figure that out, let's look at how we currently handle scheduling. Specifically, let's talk about the evolution of resource leveling.
Right, the baseline of how we plan.
Yeah. When we open up a standard tool, resource leveling is almost exclusively a human allocation and restriction problem.
Precisely. If you look at standard heuristic leveling algorithms, they're entirely focused on time and human capacity.
It's all about the hours.
Exactly. You have a pool of tradesmen, they have a finite number of available hours in a shift, and the algorithm shifts non-critical tasks around using the available float.
So that the demand for work never exceeds your peak capacity.
Right. It's about smoothing out that resource histogram.
You're capping the peak demand, so you don't have a situation where The schedule demands 50 electricians on a Tuesday, but your subcontractor only has 20 on site.
Which is a disaster if it happens in reality.
Right, and we already do this beautifully in the software, so my skepticism immediately kicks in here. If we already have the human element leveled perfectly, isn't adding every single non-reusable material into that same scheduling algorithm just going to break the model?
Not if it's done correctly.
But think about it. If I'm scheduling a concrete pour, I level the concrete workers. I know roughly the volume of concrete required. But trying to build a complex, integrated material leveling system for things that aren't the physical asset itself, that seems like a massive exaggeration of the project manager's mandate.
It seems like an exaggeration until you realize that human resource leveling and material leveling operate on completely different mathematical physics.
What do you mean by physics in this context?
Well, human leveling deals with time, and time is fluid. If a worker isn't available, the algorithm just shifts the task to tomorrow.
Okay, sure. The task gets delayed, but it still happens.
Right. But material leveling is fundamentally a system of input, output, balance, and stock.
It's a physical limitation.
Exactly. You cannot ask a liter of diesel to work overtime.
No, you definitely can't.
And you cannot reallocate a physical consumable that has already been burned. Treating non-reusable consumables as a secondary, off-schedule item, something that procurement will just quote-unquote handle based on a spreadsheet, inevitably leads to supply ruptures.
Because procurement is operating blind.
They're completely blind to the dynamic schedule.
But wait, procurement knows to buy diesel. They have historical run rates. They know generally what a site uses.
They have historical averages, sure, but an average is completely detached from the dynamic, minute-by-minute operational flow of the critical path.
Okay, I see.
The technical goal of integrating this into the schedule is to synchronize the supply and the consumption so that the physical stock remains strictly positive at all times.
Strictly positive, meaning you never hit zero.
Never. Think about the StarCraft analogy.
Oh, the video game.
Yeah, the real-time strategy game. In StarCraft, you can queue up 50 units to build. But if your supply depot is full and you are out of resources, the game literally will not let you spawn them. It doesn't matter how much time you have.
That is a great mental model. The game engine physically prevents the execution because the prerequisite material condition hasn't been met.
Exactly. If you only level the hours in your project schedule, you're just guaranteeing that a worker is available at 8 a.m.
But they might be standing around.
Right. If you do not level the materials as a hard mathematical condition for work continuity, that worker arrives at 8:00 a.m., the temporary power generator is dry, and the work halts.
So you've paid for the labor hour, but you gained absolutely zero physical progress.
Zero. You're just burning money.
Okay, I can see the logic when it comes to direct construction materials. Like, I can see that tying the structural steel, the concrete, the heavy piping to the schedule is non-negotiable.
Because if they aren't there, there's no building.
Right. If the concrete is not poured, the curing duration doesn't start, and all the successor tasks are delayed. But this framework pushes it so much further.
It goes all the way down.
It demands that we model the materials for the people who are not even physically building anything. And this brings up a really fascinating concept from the sources, the illusion of separation between direct and indirect labor.
This right here is the theoretical foundation of the entire methodology. We all know the standard industry split, right? Between direct trades and indirect overhead.
Yeah, it's accounting 101.
But the argument here is that this line simply does not exist in the physical reality of a site execution.
Let's bypass the elementary definitions for a second. We all know direct labor puts hands on tools, and indirect labor handles the planning, the quality control, the safety oversight.
Right, the support functions.
Where the framework challenges standard thinking is the assertion that indirect labor is fundamentally not outside the production process.
Precisely. The standard way of thinking treats indirect labor as a fixed overhead cost. It's like a straight line running parallel to the project.
Just a burn rate in the background.
Yeah, but the reality is that the indirect worker integrates directly into the operational dynamics of the site. The direct worker executes physically, but the indirect worker makes that execution viable.
So they enable the work.
Exactly. Without the safety release, Without the quality inspection, without the logistical coordination, the direct execution cannot legally or practically sustain itself.
Conceptually, sure, the QA/QC inspector is critical. But again, we are talking about resource modeling inside a software environment.
The math.
Right. I will argue that tracking the direct worker's welding rods is absolutely necessary. But tracking the QA/QC inspector's specific inspection dies. Or tracking the planner's physical supplies. Why do we need to model their resources on the critical path? If a topographer runs out of marking paint, they can run to a hardware store.
But it's about functional crossover. The reality of a job site loves to destroy those neat little organizational charts we create back in the home office.
Oh, absolutely. The chaos of the field.
A professional's function is incredibly fluid depending on the momentary need of the execution. Take an electrician. Normally, they are direct labor pulling high-voltage cables.
Hands-on tools.
Right. But that exact same electrician might suddenly be pulled to conduct safety walkdowns on temporary power lines before a mechanical team can even enter a confined space.
Wow. Okay. So in that moment, your direct labor just became indirect overhead.
Exactly.
Yeah.
And they are performing an indirect function that is an absolute prerequisite for other direct work to proceed.
That's a great example.
Or take a heavy machinery mechanic who usually assembles turbine components. That's direct work. They might be pulled aside to verify the alignment of a completely different system before a structural team can bolt everything down.
So the dependency link is what makes the material critical, regardless of what color badge the worker is wearing.
Yes. If you accept that the boundary is fluid and that indirect tasks are mandatory prerequisites for direct execution, then you cannot ignore the physical resources required to perform those indirect tasks.
Because they share the same ecosystem.
Exactly. If you only model the welding rods for the welder, but you do not model the penetrant testing die for the welding inspector, what happens?
Well, the weld gets completed, but the spool piece cannot be certified and handed over.
And the subsequent pressure testing cannot begin. The entire mechanical train stops.
It just cascades.
It collapses not because of a lack of direct construction materials, but a lack of indirect support materials.
All right, you have me on the inspection die. That is a direct prerequisite. I'll give you that one.
I'll take it.
But this methodology goes aggressively into everyday items, which brings us to shared inputs. The framework looks at the physical items used by both direct and indirect workers simply to exist on the site.
Because they share the same physical environment, they share fundamental subsistence and operational needs.
And here is where I really have to push back hard. When we talk about shared inputs, we are talking about human subsistence, drinking water, basic hygiene.
The basics of keeping humans alive and working.
Right. We're talking about safety protection, PPE, isolation tape, and basic operational support hand tools, radios.
Critical items.
Sure, but you want me to open a multi-million-dollar Primavera or Spider project schedule, and right beneath Commission Turbine B, I'm supposed to add a resource node for buy 500 rolls of toilet paper.
I know how it sounds.
You will get laughed out of the planning room. That is the definition of micromanagement. It clutters the data model to the point of being unusable.
It looks unusable until you experience the cascading failure of treating it as an afterthought.
But toilet paper, come on.
You mentioned the data clutter of tracking toilet paper and disposable cups. The framework actually addresses this exact mathematical concern. They know that listing hundreds of tiny consumable items fragments the work breakdown structure.
It would make the software calculation impossibly slow.
Exactly. And that is why they introduced the concept of kits.
Right, the kit methodology, consolidating the noise.
Yes. To avoid excessive database fragmentation, you group correlative items based on their practical synchronous function on the site.
So bundling things together.
A kit is a synthetic parameter. It represents elements that are statistically consumed together. It actually improves the mathematical readability of the project model.
How does that actually parameterize in the software, though? Give me an example.
Well, instead of modeling soap, paper towels, and sanitary supplies separately, you parameterize a single hygiene kit.
Okay, that's cleaner.
Instead of tracking individual hard hats, safety glasses, and earplugs for a fluctuating workforce, you model a basic PPE kit. You create a field comm kit encompassing radios, chargers, and spare batteries.
Okay, visually, hygiene kit looks a lot better on a resource breakdown structure than listing out office supplies.
It's much more elegant.
But you still haven't convinced me why this needs to be mathematically linked to the project schedule. Why can't the site administrator just keep an eye on the supply closet and trigger a reorder when it gets low? The two-bin Kanban system has worked for decades.
Because a visual Kanban system in a supply closet is entirely reactive. And a mega project operates on massive, sudden shifts in labor density.
What do you mean by labor density?
Let's look at the legal and physical reality of a site. What happens if a site with 800 workers runs out of potable water or sanitary supplies?
Well, the union reps step in immediately. Health and safety inspectors can issue a stop work order. The site is legally shut down.
Right. The capacity of your human resources instantly drops to zero. It does not matter if your man-hours are perfectly leveled. It does not matter if your structural steel arrived 3 weeks early. The work stops.
Because it's illegal to keep them working.
Exactly. Now, if you leave the restocking to an administrator eyeballing a closet, they're ordering based on the past week's consumption.
Right, looking backward.
But what if your project schedule dictates that next week, 3 new massive subcontractors are mobilizing simultaneously, spiking your headcount from 800 to 2,000?
The supply closet administrator doesn't have visibility into the 3-week look-ahead schedule. They don't know the spike is coming.
Exactly. They order the usual amount. The new workers arrive. The potable water and hygiene supplies are exhausted in 48 hours.
And the site shuts down.
But by parametrically linking the hygiene kit to the headcount curve of both direct and indirect labor inside the scheduling software.
You are predicting the consumption rate mathematically.
Yes. The software automatically calculates the increased burn rate of the kits, checks it against procurement lead times, and flags a supply rupture risk before the mobilization even happens.
So the kit isn't just a convenient grouping of items, it's an actual mathematical unit of operational viability.
That's a perfect way to phrase it.
If the schedule calculates that the unit will be missing, the software essentially tells you that the planned construction cannot physically happen.
Precisely. Water, PPE, and communication serve the project as a holistic system. If the system lacks inputs, the output, which is your construction progress, ceases.
I am actually starting to see the defense here. You are moving me on the human element because of that labor density spike problem.
It's undeniable once you map it out.
But let's shift gears from people to machinery, because humans are really only half the site. What happens when the entity eating all your resources doesn't need a bathroom break, but needs 500 gallons of diesel a day?
This is where we get into agnostic equipment. Just as we have shared kits for the workforce, a heavy industrial site relies on shared machinery that serves both direct and indirect functions fluidly.
Agnostic meaning it doesn't care what you call it.
Exactly. And the utility of that equipment does not depend on a fixed organizational label.
We're talking about the transport vehicles, the flatbed trucks, the forklifts, the mobile generators, the light towers.
All heavy lifters.
Now, traditional project management definitely tracks heavy machinery. If I have a 500-ton crawler crane, it is absolutely a resource node in my schedule because it's tied directly to lifting the turbine block.
Of course, it's prime equipment.
But a supervisor's pickup truck, a generic 5-ton flatbed, those usually fall into a generic site overhead cost account. They're almost never scheduled.
And that is a critical vulnerability. The standard practice assumes you can separate a direct production forklift from an indirect logistical truck.
And I'm going to find a flaw in the logic here because if I'm the lead scheduler, I want to know exactly where the main forklift is so the structural steel gets moved to the laydown yard. That is critical path.
Okay, follow that thread.
The QA manager can drive their pickup truck wherever they want. It does not affect the critical path. Why blend them in the resource model?
You're assuming the equipment rigidly adheres to the fixed label you assigned it in your budget. But equipment functionality on a dynamic site is completely agnostic. A machine does not care about your organizational chart.
Give me a scenario where that agnostic nature actually breaks the schedule.
Take a standard site support vehicle. Its primary budget label might be indirect. It transports supervisors for inspections.
Right.
But what happens when a critical frontline pipe fitting crew suddenly needs a specialized flange alignment tool from the main warehouse 2 miles across the site?
They call for someone to bring it.
Exactly. And that indirect support car is suddenly performing a direct critical path delivery. If that car is unavailable because we didn't model its availability and maintenance schedule, the direct work stops while a crew of highly paid pipe fitters literally just stands around waiting.
Or the 5-ton flatbed truck. 1 minute, it's moving critical structural steel direct support. The next minute, it's moving administrative porta-johns or handling waste removal indirect support.
The most glaring example is temporary power. A massive diesel generator might be powering the welding machines and the pipe threaders, pure direct construction. But simultaneously, it's powering the site safety lighting and the administrative trailers, where the planners and QA teams are working.
You cannot mathematically split the generator in half.
Exactly. You cannot rigidly tag the node as purely direct or purely indirect. The physical reality of the site mixes functions. Therefore, your technical control software must track this reality.
So you treat it as a shared node.
You must model its operational capacity as a shared network node. If the generator fails, both the direct welding and the indirect planning halt simultaneously.
Okay, I am visualizing it like a network graph now. The shared machine is a node that supports multiple diverging branches of the project tree. I get that. But machines do not run on good intentions.
No, they do not.
They run on consumables.
They require energetic inputs, lubrication, and electromechanical replacement parts. Diesel, oil, grease, batteries, filters, tires.
The lifeblood of the machines.
These are the elements that physically sustain the machines that sustain the project.
And I am going to express severe disbelief again.
I figured you would.
I understand tracking the generator node. I even understand tracking the diesel burn rate for the generator against the schedule. But are we seriously saying that a sophisticated project management tool needs to be modeling the oil filters, the fan belts, and the spare tires of the flatbed truck?
Yes.
This is fleet management. This is the auto mechanics domain. If a tire blows, the mechanic changes the tire. Why does the master project schedule care about a fan belt?
The master schedule cares because time is money, and a machine waiting for a part is a machine with zero operational capacity. Let's walk through the exact cascading mathematical nightmare of a blown tire that you think is just the mechanic's problem.
All right, let's trace it. Show me how a tire stops a mega project.
Let's go back to your 5-ton flatbed cargo truck. It is a shared agnostic resource. It's moving critical structural steel to the direct labor, and it's moving safety barriers for the indirect labor.
Doing double duty.
Right. It's running 14-hour shifts because the schedule is compressed. It blows a tire, and the primary hydraulic hose for the lifting bed snaps under the heavy load.
A bad day for the operator, but, the mechanic fixes it.
The mechanic goes to the maintenance shed to fix it.
Right.
But they find no spare tire and no hydraulic hose.
They're not.
Because the maintenance supplies were handled as an off-schedule, indirect overhead spreadsheet. Procurement was never mathematically notified that the usage profile of that specific truck was going to double this month due to schedule compression.
Oh, wow. They were ordering parts based on last month's run rate.
Exactly. So the mechanic submits an urgent requisition to procurement. Procurement contacts the vendor. The vendor is 2 towns over and has a 48-hour lead time.
That's a long wait for a critical truck.
That shared cargo truck is now hard down for 3 days. Because the truck is down, site logistics freeze. Because logistics freeze, the structural steel does not reach the laydown yard.
It's a domino effect.
Because the steel doesn't reach the yard, the 500-ton crane sits idle. Because the crane sits idle, the direct workers, the highly paid, perfectly leveled critical path workers, are standing around with their hands in their pockets.
Wow.
A blown tire on a shared vehicle stops logistics, which starves the direct workers. That is why replacement inputs are not fleet management trivialities.
They are the granular building blocks of project momentum.
If you do not model the consumption rate and the required stock of replacement inputs based on the intense usage profile of the scheduled activities, your project is flying blind into a supply rupture.
That causality chain is incredibly compelling. You were saying that the failure to dynamically model a $20 hydraulic hose on an indirect support vehicle can ripple up through the network and cause a $50,000 a day delay on the critical path.
And that is exactly why the methodology demands systematic attention to all these elements. You cannot treat them as invisible. They must enter the rigorous logic of site administration through receiving mechanisms, usage logs, balance, and positive stock thresholds.
This brings us to the ultimate synthesis of this deep dive, really. How do we actually do this? Because standard project management software like, Microsoft Project or basic Primavera P6 setups, they're not inherently built to calculate the burn rate of hydraulic hoses against a fluctuating headcount curve.
No, standard tools treat resources mostly as hourly constraints. But advanced software, specifically tools like Spider Project, allow for this exact type of dynamic, volume-based material modeling.
Let's dive into the technical mechanics of that, because Spider Project is known for having incredibly robust algorithmic capabilities that go way beyond simple Gantt charting. How does it handle a liter of diesel differently than standard software handles a human worker's available hours?
In a standard tool, you basically just say worker A is available for 8 hours.
Very static.
Right. In Spider Project, using this framework, you create a dynamic linkage based on consumption rates and cost centers. You establish an algorithm that says activity A requires 10 hours of direct heavy machinery and 2 hours of indirect support machinery.
Okay, linking the activity to the machine.
Then it goes further. It says, therefore, activity A has a parametric burn rate of 50 liters of diesel per day and a fractional wear rate on Class 3 maintenance components.
So the material demand is algorithmically bound to the activity duration and intensity.
Yes, and here is where the real synchronization happens. As the project inevitably shifts, as activities are delayed by weather or accelerated by schedule compression or as float is consumed, the software automatically recalculates the forward-looking demand curve for the diesel, the hygiene kits, the replacement filters.
It updates the required inventory levels dynamically?
Exactly. The practical algorithmic objective is to maintain the mathematical stock always strictly positive.
Never hitting zero.
The input, output, and balance must remain coherent with the executive plan. You cannot have the scheduled consumption exceed the scheduled supply deliveries at any point on the timeline.
So if the software detects that on, let's say, week 14, due to a massive influx of concurrent tasks, the burn rate of diesel will exceed the scheduled tank refills.
It flags a critical supply rupture risk. It throws a hard mathematical error before it ever happens in the real world.
That's incredible.
It alerts procurement automatically. You must increase diesel deliveries by 30% starting week 12, or the critical path fails on week 14. It transforms these recurring consumption items from reactive administrative headaches into effective, predictive elements of operational control.
Let's resolve this debate, because my initial stance has completely shifted here.
I thought I might.
I started out arguing that parametric modeling of every non-reusable material, especially the mundane indirect stuff like the supervisor's fuel or the site's hygiene kits, was an exaggeration, a bureaucratic nightmare.
Which is the normal reaction.
But looking at the cascading mathematics of it, what I viewed as micromanagement is actually a highly sophisticated predictive mechanism for risk management.
It is about understanding the physics of the site. You are not tracking paper towels for the sake of tracking paper towels.
No, you are acknowledging that a mega project is a closed ecological system. If the bottom of the food chain, the basic human subsistence, the vehicle maintenance, the shared logistics, if that collapses, the top of the food chain, the critical path construction starves. You are modeling the environment that allows the schedule to survive.
That is the perfect way to articulate it. There's an underlying philosophy here. A beautiful Gantt chart with perfectly leveled man-hours is pure fiction if the physical reality of the site cannot support those man-hours.
There's a quote from the source that really sticks out now. The schedule might be pretty, but without material arriving on the right time, it becomes just technical literature.
Exactly. Without the positive stock of non-reusable materials, your schedule is just an expensive work of fiction. This meticulous modeling integrating direct, indirect, human and machine, time and material is the only mathematical way to ensure the work never physically stops.
It is a radical, almost intimidating way to look at project controls, but when you trace the causality chain, it is airtight logic.
It really is.
If you have ever managed a project, you know the absolute terror of a sudden, unforeseen bottleneck. Today, we unpacked how those bottlenecks aren't usually acts of God. They are failures of material leveling.
Preventable failures.
We started by looking at how standard scheduling is obsessed with time and human hours, treating physical consumables as an afterthought. Then we tore down the artificial wall between direct construction and indirect overhead, showing how functional crossover means a lack of QA supplies can literally halt a massive concrete pour.
And we saw how grouping shared human needs into mathematical kits allows software to predict supply ruptures during massive labor mobilizations.
We explored how agnostic equipment like flatbed trucks and generators serve the entire project network, meaning their lifeblood, the diesel, the hydraulic hoses, the filters must be aggressively modeled against the schedule's intensity.
Because a blown tire on an indirect truck can derail a $50,000 critical path delivery.
And finally, we looked at how advanced algorithms in tools like Spider Project dynamically link these burn rates to schedule activities, ensuring that your physical stock remains strictly positive.
Turning procurement from a reactive guessing game into a predictive science.
We moved from viewing material modeling as a bureaucratic exaggeration to realizing it is the absolute foundation of guaranteed project control.
Elevating the mundane to the critical, because the critical relies entirely on the mundane.
Think about the last time your team missed a major deadline. I want to leave you with a provocative thought to ponder. We have talked entirely about heavy industrial construction today, but this framework applies to any complex system.
Absolutely any system.
Think about your own work environment, whether you are deploying enterprise software, managing hospital logistics, or running a massive retail rollout. What are the indirect, non-reusable materials in your world? What are those mundane, everyday items or shared resources that everyone ignores, that everyone assumes will just organically be there, but if they suddenly vanish tomorrow, would bring your entire operation crashing down? Are you mathematically modeling your own equivalent of diesel and hygiene kits to guarantee your success? Or is your perfectly crafted strategy just pretty technical literature waiting for physical reality to hit?